to all. So today is our first recorded lecture on Blackboard. So today's topic is degrees of freedom and commonly observed things related to degrees of freedom. Please note that degrees of freedom, as we discussed in our last class, it is the configuration which is possible that way. And for example, if, when we discussed in the last class that if you're going to consider a point in three-dimensional space, you need x, y, z, that representation, and this capital X, Y, Z is independent to each other, so that way it accounts to the degrees of freedom of 3. So a point in three-dimensional space has 3 degrees of freedom. Similarly, for a two-dimensional coordinate system, a point in 2D will be having the representation as capital X and capital Y. So as such, it will be having 2 degrees of freedom. And if you are going to consider as a special case of 2D case, as a special case of three-dimensional case, then you will find that your Z is constant. So that imposes one constant. So 3 minus 1 is equal to 2, or as such it is having 2 degrees of freedom. Now let's come to a case of a straight line in capital XYZ or 3D space. Then you can represent that in terms of x1, y1, z1, x2, y2, z2. Okay. So as such you will be having 6 minus, there exists one constant, and that constant is equal to, that constant is square root of x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square is equal to n, the length. So you are having 5 degrees of freedom. Similarly over here you are having 4 minus 1 is equal to 3. Now let us identify that in terms of physical way. So this straight line can translate in x, translate in y, and translate in z. So these 3 degrees of freedom we got. Now this straight line can rotate. Let's just choose another coordinate system. It can rotate about x, about y, but the rotation about its own axis is immaterial because there exists no dimension. So you are going to get 5 degrees of freedom. Now over here, this straight line can translate in x, can translate in y, and it can rotate about z axis. Now with this basic idea, we will be just going for degrees of freedom of a triangle in a plane. So how many degrees of freedom that your triangle is going to have? Yeah, you think? So what you are going to get is all these 6 are going to make all these 6 points. There are 6 points minus, let us identify the constant. So what are those constants? Those constants are this length is going to be same, or rather if you just mark them as ABC point. So what you are going to get, AB length is not going to change, that is one constant, minus BC length is not going to change, minus one constant, minus CA length is not going to change. So you are essentially having 3 degrees of freedom. Similarly, let's think about a rectangle. So you just mark them as capital X1, Y1, X2, Y2, X3, Y3, X4 and Y4. So how many degrees of freedom that this rectangle is having? DOF is equal to, what you are going to get? So you are having 4, 2, 2, 4, 6, 8. 8 minus, what are those? The length. This length is not going to change, this length is not going to change, this length is not going to change, and this length is not going to change. So if you are going to mark them as A, B, C and D, AB length is not going to change, BC length is not going to change, CD length is not going to change, CD length is not going to change, and DA length is not going to change. So it is having 4 degrees of freedom. Now let's say that instead of doing all these degrees of freedom, we need the constant. Constant means the things is not going to move, which is restraining the motion. That is we are describing as constant. For example, if you want to restrain completely a triangle, then what you are going to do? Or let's say you are working in a plane, so it has any planar motion. Now look carefully that this triangle is having 3 degrees of freedom. A straight line was also having 3 degrees of freedom. So it means that a planar body, now you are coming to a plane motion. The motion is occurring in a plane. So for a planar motion, what we are going to get is that we are having the degrees of freedom possibly is equal to 3. The degrees of freedom possible is 3. So these 3 degrees of freedom are to be identified as translation in x, translation in y, and rotation about z. For simple example, if I am going to restrain it, I need 3 constant. So I need 3 constant force to make it fixed or in static equilibrium. Now, for example, let's consider, you just take this triangle, you just take this triangle. So these 3 constant forces are what? It could be like this, it could be like this, and it could be like this. So you are going to get R1, R2, and R3. Now look, these 3 constant forces are sufficient to place the triangle in a plane, or as such, it's equivalently you can write or you can draw as if this triangle is somewhat like this and it is having a roller support. Yeah, is it so? Now by mistake, if I am going to make this configuration, so I am going to make this configuration somewhat like this. And its equivalent form is So what does it mean? What these 2 figures are going to mean, that a triangle which is restrained in a plane, you need 3 forces, 3 constant forces. They are R1, R2, R3. And as such, you can describe this whole thing as like this. But when you are going to make the fixed support in both the ends, the triangle is fixed. But what you have done is that you have invited 4 reaction forces or the 4 constant forces. So as such, it is called over constant. Over constant means what is not required. Out of these 4 forces, one force is redundant. It is not required at all. So if you are going to make 3 forces, if you are going to give 3 forces to a triangle, then it is not going to move. Okay. So the motion, all these possible motions along x, motion along y, and rotation along z across about z is going to be restrained. These 3 forces are good enough. But when you are making 2 support as fixed, then it is called the over constant. We don't need this part. Now what is the example of it? Will be coming over here. Now let us do a similar exercise with this. Let's do a similar exercise with this. So for a planar motion, let's say, so we will not be over constraining it. Let's do this exercise. A fixed support and a roller support. Okay. So essentially, we can draw this as the same diagram as there are reaction R1, R2 and R3. So we are talking now about the planar motion, the motion which is occurring in a plane. For a planar motion, I need 3 reaction forces to restrain the whole body. The body is not going to move. Now in this case, in the previous part, we found that the degrees of freedom 4. Okay. Now what is the other motion it is going to occur? Which is the other motion? We are going to get 3 constant forces, but the degrees of freedom over here is 4. So 1 degrees of freedom is not being constant. What is that? Let us identify. You think and tell me. So I am just going to give a pause of 2-3 minutes. You think about this. Is the question clear to you? For example, as I mentioned that in a planar motion, 3 motions are possible. So I need 3 constant forces to make it not to move. And these 3 constant forces are R1, R2, R3. So for a planar motion, these 3 constant forces are not going to change. Either you can take the moment or the force, whatever the way you choose, but you are going to get 3 distinct. So these 3 distinct part we got over here, and this is just a usual representation. Based on this, I made over here 3, I got 3, but one part is not being constant or restrained. What is that? Yeah, this thing, and after 2-3 minutes I am going to discuss. Okay, so what have you thought? First thing is over here your R1, R2, R3 are there, right? So these 3 constants are not going to change. You cannot over constant it. But what the other motion is having is that this point can move down this, or it is going to change its relative position with respect to this. This means this rectangle could become somewhat like this with this, that of the constant forces. This rectangle can take the shape of like this. So this is one possible motion which we have not restrained. In order to restrain it, what shall I do? I will make another straight line over here. Now tell me how many degrees of freedom if I am just going to change this part. For example, this rectangle is now being changed to this. How many degrees of freedom that you are having? Essentially, we will be having DOF is equal to 3. Just check. So you have how many points? 1, 2, 3, 4. 4 into 2, 8, minus this length 1, this length 2, this length 3, this length 4, this length 5. 8 minus 5 is equal to 3. Now, what you are getting out of it? So we will be coming to our second objective of this lecture is we will be learning the degrees of freedom, and we will be observing the application of degrees of freedom in many commonly observed cases. So what you have made? You have made two triangles. From a rectangle, you have made two triangles, right? So when you have made two triangles, essentially what you are doing? You are taking the base element as a triangle. Okay? So what it implies? It implies that in the commonly observed things, or all these bridges, the high tension cable tower, railway bridges which are made of steel, they use called the star structure that you have studied in your first year. So a star structure always is having the triangle as its building block element, not the rectangle. If it is going to be the rectangle, then the stress is going to fall. So you can consider a stress which is, of course it is a 3D body, but when you are doing the analysis in a plane, kindly look that any kind of bridges made of straws or any kind of high structured building, structural things which are made up of straws, you can consider they are composed of various planes. Now all these planes are made up of triangles. The basic element is a triangle. So why? Because they are not going to collapse. If it is rectangle, then they are going to collapse. We cannot build it. Okay, sure. Now with this idea, let's come to our topic is that we are going to make the rigid body. We will be building the rigid body which is made up of. Now we are entering into the 3D kinematics. We will be calling it as kinematics because we are dealing with the motion. So far we have not talked about the forces. We are just considering the motion. So we will be talking about the 3D kinematics part. For 3D kinematics part, we will be defining rigid body. The definition of rigid body. The definition of rigid body is that there is no relative change of change of relative distance change. There is no change of relative distance there is no change of relative distance between any 2 points. Okay, so let's take a point in the 3D kinematics. So it is having x1, y1 and z1. Now you are going to take another point. Point is having 3 degrees of freedom. Okay, so we are choosing another point. Let's say it is x2, y2 and z2. Let's say another third point, x3, y3 and z3. So you just join them through a line, because that is what the rigid body is to be constructed. So how many degrees of freedom this triangle is going to have? Because we are taking 3 points, right? Or we are going to start with the n number of points. We will be going up to the n number of points, but we are going to start at first with the 3 points. So the rigid body definition is telling that there is no change of relative distance between any 2 points. So you have made x1, y1, z1, x2, y2, z2, x3, y3, z3. Now in x, their relative distance is not going to change. So what you are going to get? 3 DOF is equal to 3 into 3 is equal to 9 minus, how many constants are there? There are 3 constants. This length is not going to change, this length is not going to change, and this length is not going to change. So you have minus 3, 3 into 3 minus 3 is equal to 6. Now let us choose another point. Let's say you mark them as A, B and C. You choose another point D, which is of x4, y4 and z4. Now, as per the definition of rigid body, they are not going to change their between any 2 points. So I am going to make this. I have to make fixed this point with respect to these 3 points. So I made it. Now how many degrees of freedom that we are having? Is equal to 3 cross 4. We have taken 4 points minus, how many constants that we are having? 1, 2, 3, 4, 5. Minus 5 is equal to what? 7. Now let us check that whether any 2 points this definition is been satisfied or not. Now let us take, let's say this point is D. Now is the BD distance is fixed? You have a think? Is BD distance is fixed? What will be your answer? Yes, you think? Is BD distance is going to change? Of course it is going to change. How? Making AC as the axis, this D part can rotate like this. If it is going to rotate, then it is going to change the distance with respect to B. The definition is telling that any 2 points, the relative distance is not going to change. So D point is not fixed. If it is going to rotate with respect to keeping the AC axis, then what the motion is going to be? D is going to be like this, perpendicular to this. It is going to come out of the blackboard. So you have to make another straight line joining B. So minus 1 is equal to 6. Now choose another point. Let's say this point is E. So you do the same exercise, join them together. Now once again, what is going to happen is that this E point can rotate about this. So you have to fix it. Either you can connect it to D or you can connect it to A. So what the degrees of freedom is going to be? DOF is equal to 3 cross 5 minus, How many constant that you are having? How many constant that you are having? Minus 9 constant that you are having. Count them. For this triangle is 3 minus these 3 constant and along these 3 constant. So 9, 3 for this triangle, 3 for this point, extra point, for 3 another extra. So it constitutes 9. Now if I am going to make F, another point F, once again I am going to take 3 constant and I am adding 3 points. So with this, if you are going for n number of points, so you are going to make 3 cross n, 3n minus how many constant that you are going to get? Minus how many constant you are going to get? 3n minus 3 for the base triangle. Okay? Minus how many? N minus, please use the method of induction. 3 for the base triangle minus n minus 3 into 3. So how many it is? It is equal to 3n minus 3 minus 3n plus 9 is it going to be 6. Okay, so is it clear now? So as such, if I am going to take infinitely many points within a rigid body, the degrees of freedom is going to be 6. Okay, if I am going to take infinitely many points, the degrees of freedom is going to be 6. Now let us identify about this. What are the motions? The motions is translation along x, translation along y, translation along z, and rotation about x, rotation about y, and rotation about z. Okay, so this is what is the degrees of freedom of a rigid body. Now out of all these calculations, whatever we have done, from there can we draw any conclusive picture, or can I write any conclusive statement? Let us try. Any three non-collinear points in the body is sufficient to represent a rigid Now I am going to ask why I have used these non-collinear points. Because if you are going to take all the 3 points as collinear, for simple example, so there are A, B and C points which are collinear. If this is collinear, then degrees of freedom is equal to 5. So it does not represent the rigid body, rather it is representing a straight line. So for any rigid body, if I am going to choose this as your rigid body, what I will be doing is that I will be just marking 1, 2, 3. A, B, C point, any 3 points which are non-collinear, that these 3 points is sufficient enough to represent as a rigid body. Okay? Now let us come to a simple case. Let us remove the rigid body assumption. Let us remove the rigid body assumption. Let's say it is the deformable body which you have studied as a strength of material in your engineering mechanics course, because you have studied all these stress, strain and all these analysis, diagrams and all these things. Now let's say it is deformable body. So a deformable body will be having n number of points. A deformable body over here, the distance is not fixed. They can change. They can change their relative position. Any 2 points. Okay. So how many degrees of freedom that a deformable body is going to have? Yeah. So if it is composed of n number of points, then it will be having the DOF is equal to 3n. It will be having 3n degrees of freedom, because any 2 points are not going to, they are not fixed, they are not supposed to change, they are supposed to change their relative position, any 2 points. So as such we are having 3n degrees of freedom. Now example, for example, if I am going to consider, you understand n is quite large, n is quite large, then we will be coming to the continuum concept. What this continuum concept is? It tells that if you are going to choose a point within a deformable body, let's say this is what is a deformable body. If you are going to choose any point, vicinity to this point, there are infinitely many points. As such, the whole body is composed of infinitely many points. If you are going to choose a particular point, vicinity to it, there are infinitely many such points. Now to understand this concept, let's say if I am going to say that in the number system you have the integers. How many integers that you are having? 1, 2, let's say positive integers, 1, 2, 3, 4, 5, 6, infinitely many. Now in a similar way, if I am going to say in the number line from 0 to 1, how many real numbers are there? You are going to say infinitely many. But these two infinities are not same. For example, if you are going to choose 3 in the integer, let's say 1, 2, 3, 4, 5, like that. So if you are going to make the inverse mapping, 1 by 2 it is there, 1 by 3 it is there, 1 by 4 it is there, but 1 by 4.5, or rather over here 4.5, if I am going to make 4.5, this is not there, but 1 by 4.5 is over here. Are you understanding? So this infinity is continuous infinity and this infinity is the discrete infinity. So whenever we are defining a deformable body, we consider that this continuum concept is valid. That means around a point, vicinity to it, there are infinitely many points are there and they constitute the deformable body. Okay, so we will be concluding over here. So out of this lecture, what we are going to take away to our home is that we discussed degrees of freedom. The degrees of freedom is the way the motions are possible. Okay, and we found that a point, particular point in 3-dimensional space is having 3 degrees of freedom because over there the x, y, z are linearly dependent. For a straight line in 3D, it is having 5 degrees of freedom. We calculated geometrically and we demonstrated in the physical motion as well. A triangle in space is having 6 degrees of freedom. The same triangle in 2D motion is having 3 degrees of freedom. And in a planar motion or 2D motion, there could be 3 possible motion. So if you are going to consider any if you try to restrain any planar motion, you need 3 reaction forces. Okay. So if you are going to make it 4, then you are over constraining it, right? So over constraining is not necessary. This 3 is sufficient to restrain the body movement. Okay. So based on this, we concluded that while our stresses, which are commonly observed in railway bridges, high tension cable structures, or any kind of civil structure made up of steel, in the platform you are going to get. So all these are, the best element is triangle, because it is the least possible way to restrain it. Okay, so with this idea we are just going to conclude it. Montu ji. Okay, thank you.